Welcome. Thanks for joining us. My name is Haley Ross, and I work for the Columbia Mountains Institute of Applied Ecology, or CMI for short. And I join you today for our 6th season of CREDtalks. CREDtalks stands for the Columbia Region Ecological Discussions. This season of CREDtalks will explore the theme of climate disruption in the Upper Columbia Basin. We're going to welcome 8 scientists to address projected impacts, potential for adaptation, and what we can do with ecosystems that may in fact contribute to mitigation. If you're in attendance today, you've likely seen the impressive list of speakers to come. If you're reviewing this recording at a later date, I encourage you to visit the event webpage to learn more about the full suite of talks in this series. You can find that information at cmiae.org. You'll see it on the top right-hand side of your screen there. Today, we will welcome Dr. Mel Reasoner, who I'll introduce in more detail in just a moment. The CREDtalks are financially supported by the Columbia Basin Trust. We share our gratitude to them for providing the funds needed to get this series off the ground. This series is also generously supported by all of you. Without your donations to this project, or without your donations, this project would not be possible. So thank you very much. We also send out a thanks to anyone who's reviewing and recording at a later date for any donations that may come our way to support the production costs with the CREDtalks series. Now, before I go any further, I'd like to acknowledge the 4 nations on whose territory I broadcast from today in Revelstoke, BC. The Sinayaks, the Tanaha, the Sequapum, and the Silks. Now, I'd actually like to invite all of you to make an acknowledgement as well, and you can do that using your chat feature. So please feel free to let us know whose territory you're zooming in from today. You could introduce yourself if you like, and then share your land acknowledgement. If you're looking for the chat and you haven't been on Zoom in a little while, or perhaps not at all, you'll find the chat icon on the bottom control panel on your screen. So if you just hover your mouse at the bottom there, click on chat, and your chat box will open. And this will be a great way to test out your chat. All right, now, as those acknowledgements start to flow in, I'm going to use this time to take the opportunity to tell you a little bit more about, or a little bit about the host organization, CMI, so the Columbia Mountains Institute of Applied Ecology. We're a nonprofit organization and an association for people working in the various fields of ecology. Our home range is southern British Columbia, Canada, but increasingly we're seeing membership from across BC and into Alberta, the Yukon, and the Northwest Territories. One of the main things we do is provide professional development opportunities in the form of conferences, courses, and webinars. Some examples from the last couple of years include a variety of statistics and stats theory courses for ecologists, field-based courses such as advanced field ornithology, soils description and identification, amphibian inventory and monitoring techniques, and various plant ID courses, and some conferences that explore more complex topics like ecology of regulated rivers, incidental take of migratory birds, and the assessment of camera trap surveys for wildlife monitoring. Our website, of course, is the best place to learn more about the things we do, and it contains great resources such as proceeding documents from all of our larger events. Again, you can find those at cmiae.org. Our typical audience is well captured by the people who have registered for this event, whereby I see representatives from environmental consultants, academics, students, industry representatives, nonprofits, First Nations governments, and provincial and municipal resource managers. All right, thank you for sharing those acknowledgements. Now, with that little bit of information about CMI shared, I'd like to move into just some nitty-gritty details and some quick Zoom orientation information for you. I think for the best experience today, I would recommend you choose speaker view to take in the webinar. The webinar is being recorded and will be posted to the event page within 1 week. Again, you'll be able to find that on our website. In this webinar format, attendees cannot turn on their cameras, So if you're trying desperately to turn your camera on, you're not going to be able to. And everyone's been muted for the presentation. If you would like to be unmuted for the Q&A session at the end, please use the raise hand function, and then we will turn on your audio. So if you hover your mouse at the bottom, again, you'll see that control panel, and you should see a little hand, raise hand. So I'll click on it now, and you can see that I have a little hand that shows up in the participant list or on my video screen there. And that will indicate to us that you would like to speak. You can also lower your hand if you've changed your mind. So you would just click on that icon again. So I'll revisit that later. The chat feature is enabled, as you saw, and this is an opportunity and a space for you to share resources and such with one another. You can use the chat to send messages to everybody, or you can private message anybody in this group. You can private message myself or CMI Tech if you're having any technological issues that you would like us to help you with. Nicole Trigg is the face behind CMI Tech. She's here to help ensure for a smooth technological experience for us. Thank you, Nicole, for joining us on your lunch break. Please note that we won't be using the chat to take questions, however, for the Q&A. What we're going to use instead is the Q&A function. So again, directing you to that control panel at the bottom of your screen, you can click the Q&A, and you will have a Q&A box that pops up. And you'll see in that box an opportunity to pose your questions. You can add your questions to that Q&A box as they come to you, but we won't actually address the questions until the end of Mel's presentation. Using this function, there is a fun feature where you can actually upvote each other's questions. So say, for example, I ask a question that you would also like to know the answer to. If you hover your mouse over my question, there'll be a little thumbs up icon that appears. And you can click on that, and that will indicate, that'll raise those questions that have been upvoted to the top of the list, and we'll make sure that we address those first. So Renee, I know you're in the audience. I was wondering, just for demonstration, if you wouldn't mind popping some sort of question in that Q&A box right now so that people can see what it looks like. Or anybody for that matter could do that. And then as soon as she has a question that pops up in the Q&A box, I'm wondering if someone can go ahead and upvote that again so that people can see what that looks like. I'm not seeing that a question is popping up, so maybe we'll revisit that at the end for the Q&A session. Okay. Oh, there we go. Kevin Bolivar, thank you. Says, how are you? Oh, and we've got some thumbs up. Perfect. 3, 4. Fantastic. Thank you for jumping in there. So that's just an example of what that Q&A box is going to look like. And clearly, that's a very important question. With 15 likes already, we're going to ask that one first. Okay, great. So moving on, it's time to get into the whole reason why you're here today. I'd like to welcome Dr. Mel Reasoner, who is going to present an overview of climate change in southern British Columbia, climate history, climate projections, and the scope of the problem. Mel Reasoner is currently involved with the Climatic Resource Consulting Climatic Resource Consulting, a research-based consulting company that has been assisting communities in Alberta and British Columbia with climate resilience planning. Over the last decade, Mel has worked for the Columbia Basin Trust Climate Action Programs, the All One Skies Climate Resilience Express, and the Fraser Basin Council's activities with First Nations communities in BC. He directed an international initiative sponsored by the Swiss Academy of Science that focuses on global climate change issues in mountain regions worldwide. Of course, this list goes on, but we won't go into all the details here. We are fortunate to have Mel with us today. Welcome. Mel, I'm going to pass it over to you. So there we go. I just unmuted you, Mel.
Great, thank you very much. Thanks for the introduction and welcome everybody. Thanks for dropping by today, and thanks to Haley and CMI for putting this together. What I think is going to be a great series of talks about climate change in this part of the world. So I'm going to dive right in here and share my screen. And hang on a sec. let's see here. Okay, so now you should see my blue screen. And if we do this correctly, I've got the wrong one. Oh, rats. I'm sorry. Here we go. This is going to come along in a second here. This is better. Okay. There, that's what is this turning up okay at your end?
Yes, it looks perfect.
Okay. So yeah, so today we're going to be talking about climate change in this part of the world. And I'm going to be talking about, first of all, a quick introduction to trend and variability with respect to climate, followed by the regional climate history of this part of the world over the last century. Then we'll look at local projections of future climate in this part of the world. And lastly, I'll venture into the big picture and are we heading in the right direction, which will involve a bit of a broader perspective, more of a global perspective, and how that relates to our part of the world. So to start off with a little bit about trend and variability, I'm going to start off with a bell curve here, looking at Northern Hemisphere land summer temperature. And we're looking at the period 1951 to 1980 here. And it makes a pretty nice bell curve. You can see a third of the years these are summers. A third of the summer temperatures are cool, a third are hot, and a third are sort of normal in the middle of the bell curve. And what has happened since 1951 to 1980, since that period, is that this bell curve has been shifting to the right because things have been warming up. This is 1983 to 1993, 1994 to 2004, and then 2005 to 2015. And you can see where we initially had about a third of cold, normal, and hot. Now what we've got is about 80% of the summers are hot relative to that 1951 to 1980 base period. And about 15% of the summers are extremely hot and off the tail of that historical bell curve. And this is where you start to run into problems in a lot of ways, because most built and natural systems are designed for or adapted to conditions underneath the historical bell curve. And when you start to get beyond the tail of the bell curve, you often start to run into trouble. And we'll be looking at a few bell curves as we proceed here. So I also want to talk a bit about variability. This is variability over time, and this is a climate record. And the first thing you notice is it's very spiky. There's a lot of variability. And you know, we tend to be somewhat distracted by that variability. Often we'll be focused on, was it a really hot summer or a cold winter? And what we're missing is the underlying trend, which kind of tends to sneak up on us a bit. But when we're talking about climate change, it's that underlying trend, not the variability. That's the important thing, the really important thing. And we need to be thinking about the long-term major shifts in climate that are multi-decadal to century scale. So that's variability over time, and we also need to think about spatial variability a bit. Now, here's a map of the world in July 2018. And the top right, it shows that it was 0.84 degrees warmer than July's in that 51 to 80 base period. And in our part of the world, it was warmer than that. It was pushing 2 degrees warmer. And we had a very hot summer 2018, and we had lots of forest fires. But that wasn't the case all over the world. If you happened to be in Chile or Argentina, you might have thought, boy, things are cooling off. It was cold down there. So that additional warmth, that additional 0.84 degrees Celsius, is not evenly spread over the planet. It's bunched up into warm blobs and cold blobs by the Earth's weather systems. Now, if we fast forward to February 2019, just a few months later, in our part of the world, in North America, it was really cold relative to the rest of the planet. And it didn't take long before the headlines started to appear in tweets and Twitters from various people. What the hell is going on with global warming? Please come back fast. We need you, etc., etc. There were a lot of these types of comments. Well, global warming didn't stop. In fact, February 2019 was 0.94 degrees warmer than February's in the base period. Again, it just wasn't evenly distributed over the planet. In our part of the world, it happened to be quite a bit colder. But global warming had not gone away. So just because it gets cold, just because there's cold extremes from time to time, doesn't mean that it's stopped. Lastly, here's a map just from this past summer, July 2021. And you can see that, you know, we can see the heat dome in July. It persisted, you know, late June through July in our part of the world. and caused all kinds of problems. And it was 0.91 degrees warmer than July's in the historic base period. And if we look at July's in this part of the world, and this is an example from Nelson, BC, you can see the coldest years. Well, each year is a blue bar, and there's a bell curve that's fitted to that. And you can see the coldest years in terms of July were down in the teens, and the warmest years were, up around 23. And July 2021, there's a 20th century mean. There's July 2021, which is 4.8 degrees warmer than the mean July's, and off the tail of the historical bell curve, the 20th century bell curve. And there were problems associated with the heat dome. So now I'm going to dive into some local climate history, and I'm looking at the southeast corner of British Columbia, and this is also the Southeast Fire Center, roughly speaking. And there are 13 climate records that I've pulled together here. Most of them are quality controlled, Environment Canada climate records, AHCCD records, and I've augmented that with a couple of records based on raw data. Kootenay Westgate, I think that's the only one that's based on raw data. And pulled these all together, and this is what it looks like in the southeast corner of BC in terms of mean annual temperature over the last 100 years. It's been increasing at a rate of about 1.5 degrees per century, or 1.5 degrees over the last 100 years. And you can see the individual stations there are in the fine lines, and the mean is in the thick line. And although they're not the same, you get the same story from any of the records. If it's a hot year in Golden, it's a hot year in Grand Forks, and so on. And if you look at the last 50 years, that rate of warming has ramped up. And this is something that you see throughout Western North America, that things have been warming up more rapidly over the last 50 years than over the last 100 years. In terms of precipitation, mean annual precip has been going up over the last 100 years, but that was largely in the early part of the century. In the last 50 years, it's more or less flattened out. But it gets interesting when we start looking at seasonal precipitation. And this horrendogram is a bit hard to look at, but I've tried to simplify it by highlighting the trends in bold. And you can see that over the last 50 years, spring in orange and spring in orange and fall in yellow, precipitation has been increasing in those two seasons, and that in winter in gray and summer in blue, precipitation has been decreasing. And when you look at those really low precip years in the summer, they're all fairly recent. We just isolate summer here, and you can see the 2003, 2017, 2018, 2021 were very dry years. And I think most folks in this part of the world will recognize that those were also bad fire years. So we can explore that a bit more by looking at precipitation and temperature on the same graph. And we're looking at June, July, August precipitation and temperature. So on this axis, we've got increasing precipitation. On this axis, we've got increasing temperature. So up in this quadrant, we've got cool, wet summers. And down in this quadrant, we've got hot and dry summers. And here's all the years from 1945 to 1999, sort of the last half of the 20th century. And if we look at the 2000s, the years since 2000 to 2021, they're in red. And you can see that they pretty much plot on the hot side of the 20th century mean for temperature. And most of them are in the hot and dry quadrant. They tend to be fairly dry as well, sort of moving into the hot and dry quadrant. And these are the years in the Southeast Fire Center with the lowest hectares burned, and these are the years in the Southeast Fire Center with the highest hectares burned. And in terms of hectares burned in the Southeast Fire Center, the top three are 2017, 2003, and 2021, deep into the hot, dry quadrant. Now, there's a lot of factors that go into why we have forest fires, but clearly climate is one of them. And we all sort of know this intuitively. If you have a cool, moist summer, it's really hard to get forest fires going. But if we have a summer like last summer where it was hot and dry, it's ripe for wildfire conditions. I'm going to skip through this one. That wasn't supposed to be there. So now we're looking at some extremes. We're looking at maximum annual daily temperature, and I've chosen Nelson as an example. So we're looking at extreme temperatures. And here's the 20th century mean for maximum daily temperature in each year. And here's 2021. It's 5.6 degrees above the 20th century mean, pushing 3 standard deviations from the 20th century mean. And again, it's off the tail of the historical bell curve and caused all kinds of problems. Now, in terms of precip, it even gets wilder. And here's an example from Kaslo. There's the 20th century mean, and this is the maximum one-day precipitation in the year of 2013, which is way beyond anything experienced historically. And this is difficult for the models to capture because often the models, when we get into projections, the models they're not really designed for individual convective storms or individual storm cycles. But this sort of thing has been popping up more frequently, and I don't think there's a month that goes by now where there isn't a report from somewhere in the world that there has been an extreme precipitation event and all kinds of flooding associated with it. And this makes sense from a scientific perspective because the warmer it gets, the more moisture you can have in the atmosphere, and what goes up must come down. So you end up with more intense precipitation events. Are we able to see some of the changes that are associated with the increasing temperatures in this part of the world? And there are some obvious ones. Receding glaciers. And we've got this pretty well nailed because we've got photographic evidence. The top picture is the Robson Glacier in 1911, and the bottom picture is the Robson Glacier in 2011. And that's how much the Robson Glacier has receded over a 100-year period. But, clearly, yeah, the big glaciers are receding, but what's really quite stark is the recession of the mid-elevation glaciers. And here's an example from just north and west of Kaslo on Marion Peak, I believe. There's the existing ice, and it's pretty easy to pick out the little ice age moraines, which are only about 100 years old. They're down there. That's how much ice has receded from these glaciers over the last 100 years. And the bottom line here is that there's not many years left in the life of these glaciers, and there's many more mid-elevation glaciers that are in just as bad shape as this. And Brian Menounos, I think in the next talk, will be talking more in depth about glaciers in this part of the world. Also, we're noticing that the fire danger situation in the province is increasing, and we're seeing more maps that look like this, August 12, 2017, where most of the province was extreme fire danger rating. And when we looked at hectares burned in the province, the wildfire situation in 2017, 2018, and 2021 set records for the highest area burned. And this is clearly an increasing problem. And Mike Flanagan will be diving into the details of this in this series as well. But something I don't think anyone saw coming was just how bad the smoke issue is going to be. Clearly, the risk of interface fire has gone up, but the effect of smoke is really widespread. And if this continues, which it might, this spells, I think, pretty bad news for tourism in BC in the summer, because it won't take long for people to figure out that there's no point in going to BC if you can't see the mountains. Also, there are some really significant health risks associated with this smoke, and in many cases, the air quality health index was above the high risk levels by a lot for many communities in BC last summer. So yes, we are seeing the effects of climate change already. Now, before we get into the local projections, I want to talk quickly about some things about climate models. And the first climate model was published in 1896 during the 19th century, except they weren't using a computer. Svante Arrhenius was using a pencil. But based on what we understood about the interaction of carbon dioxide in the atmosphere at that time, he projected if you double the percentage of carbon dioxide in the atmosphere, it would raise the Earth's temperature by 4 degrees Celsius. Modern climate models are about 3 degrees Celsius, so both were pointing in the same direction. Basically, the fundamentals were understood in the late 19th century, and since then we've basically been refining the details. But this idea of putting carbon dioxide in the atmosphere and that the climate will warm, this idea has been around for a long time, and it's pretty well verified now. Arrhenius also projected that if you increase carbon dioxide in the atmosphere, you would get an amplification of warming in the Arctic, which is a feature of most climate models. So climate models have gotten a lot of bad press, it seems, in recent years, and the bottom line here is how well do they reconstruct the observed climate over the last 100 years. And it's not perfect, but it's pretty good. And there were periods of time where the models were increasing faster than the observed, like the 10 years after 1998. But there were also times, like, for example, in the late 30s, early 40s, where the observed was higher than the models. So it's not a perfect match, but it's a pretty good match. And this gives us a crystal ball to assess what we might expect in the future. Also, the models are run with carbon dioxide in the model and without carbon dioxide to see the difference. And if you look at the blue curve on the bottom and the range of variability associated with it, that's the simulated climate without carbon dioxide in the models. And then the orange curve on the top is what you get when you include the carbon dioxide in the models, and then the black line is the observed. And the only way you get that match is if you include carbon dioxide in the model runs. So one of the big uncertainties about which models or how much it's going to warm in the future is which emissions pathway we follow into the future, and the models are based on that. So here's a high emissions reduction model, or a low carbon emissions model, where carbon reductions meet the Paris Agreement goals, and that would get us to below 2 degrees Celsius. Here's a less aggressive carbon reduction pathway, a low carbon pathway. Roughly speaking, this pathway gets us to what our Paris Agreement pledges are. So there's a difference between the Paris goals and what we've committed to. And then there's sort of a business as usual scenario on the top here, which would get us to more than 4 degrees Celsius above pre-industrial. So the models that I'm going to be showing you, the model projections, are based on, I'll show you a low carbon pathway, not the most aggressive, not one that keeps us below 2 degrees, and then a high carbon pathway. And we're looking at temperatures globally of 2.5 or 4 degrees Celsius, those types of numbers, which don't seem like a lot, but this is where Earth history gives us some perspective. We're looking down on the North Pole on the left during the last glacial maximum about 20,000 years ago, and on the right we're looking down at it today. And this is a difference between a full glacial state, an ice age, and an interglacial state, which is the current situation. And the global temperature difference between these two states, between full glacial and interglacial, is something in the neighborhood of 4 to 5 degrees Celsius. So when we're talking about global projections of 2 to 4 degrees Celsius, that's significant in terms of what can happen to the planet. So I'm going to jump into some local projections here, and I'm going to start off with an example using Cranbrook. So here we're looking at mean annual temperature projections for Cranbrook in yellow. The historic is in black, and you can see all the individual model runs with the fine lines, and the model ensemble mean is the thick yellow line. And this is the model results you get if we're following the RCP 4.5, which was that lower emissions pathway that I highlighted earlier. It's not the most aggressive carbon reduction pathway, but it is a fairly aggressive carbon reduction pathway. And that gives us about 2.6 degrees warming mean annual temperature by the 2050s. And that is relative to the 1961 to 1990 base period. So some of that warming has already been realized. So that's the low carbon pathway. Not the lowest, but a low carbon pathway. And here's what happens if we end up following the high carbon pathway. We end up with 3.3 degrees Celsius warming by the 2050s. Okay. Here's an example. I'm using Nelson in this example, but I just wanted to show that the other thing that is likely to happen as we move forward is that the bell curves may flatten out. And this turns up in many of the projections. You can see the historic bell curve in gray, and it's fairly tight. But as we move forward, to the 2050s, and then towards not the 2050s, the early part of the century, the latter part of the century. As we move forward in time, that bell curve flattens out a bit more. And what this means is that, the mean is increasing, but there's less change in the cold extremes, but there's even more change in the high extremes. Okay, in terms of mean annual precipitation projections for the Cranbrook area, we're looking at an increase of about 6%, regardless of which emissions pathway we follow. So an increase in mean annual precipitation. But when we break it down by seasons, we can see that winter precipitation is expected to be almost twice that. So 11 to 12% more winter precipitation by the 2050s. And winter temperatures are projected to go up by 2.7 to 3.1 degrees Celsius, depending on which emissions pathway we follow. So this sets up a situation where we're getting more precipitation in the winter, but in the valley bottoms, it may come as more of that precipitation may come as rain rather than snow. Not always, but we're likely to get wetter conditions, rainier conditions in the valley bottoms, more rainy conditions. And it may end up that we actually have higher snowpacks at the higher elevations, where it's never cold enough to rain. In terms of summers, the temperatures are projected to go up between 3 and 3.9 degrees Celsius by the 2050s. And summer precipitation, both high and low emissions pathways are projecting a decrease in summer precipitation of up 10% or so, which should be a big red flag for wildfire hazard. And then going back to this diagram that I had up earlier, where we have precipitation on one axis and temperature on the other axis, and the areas burned in low in blue and high in red. If we look at the projections, here's the mean for the last half of the 20th century. Here's the 2000s, and with the low end, the low emissions pathway, the RCP 4.5 pathway, emissions pathway, that's what that looks like by the 2050s. So the bottom line here is projections for summer precip and temperature are taking us further and further into that hot and dry quadrant. In terms of precipitation, maximum precip annual was in the usually less than 10%, but maximum one-day precip is projected to go up more than that. But this is getting difficult for the models to handle, and in many cases, the observed maximum one-day precipitation already exceeds anything in the model projection. So this is a particularly tough one for planners. But we can anticipate that the intensity of the precip is likely to increase from the basic physics of having more water vapor in the atmosphere. Looking at extreme temperatures, now we're looking at projections of the maximum one-day temperature, and I'm using Nelson as an example, and you can see the historic record. There's the maximum one-day temperature ever recorded in Nelson was 40.7 degrees. That was last summer. And you can see as we go forward with the low emissions pathway, the RCP 4.5 pathway in the future, this is likely to happen again in the future. But if we follow the high emissions pathway, it's almost certain to happen again in the future. And some of the work that we've been doing with our company, the Climatic Resources Consulting, is trying to quantify this. And so what we're looking at on the left graph is the low emissions pathway in blue, the high emissions pathway in orange, and the probability that we will exceed 40.7 degrees Celsius by the 2050s on an annual basis. And it turns out to be, if we follow the low emissions pathway, 3%, and 10% if we follow the high emissions pathway. So this could be useful for planners if you're dealing with annual budgets that are associated with things like cooling of buildings. But if you look at what is the probability of that occurring once before the 2050s, then it's significantly higher because you're rolling the dice many more times. And if you've got infrastructure that fails or operations that fail, if they exceed a temperature threshold, this would be useful for that sort of analysis. And you can see that by the 2050s, there's a 70% chance that we'll exceed that 40.7 degree threshold if we follow the high emissions pathway, and a 34% chance if we follow the low emissions pathway. Okay, so sort of wrapping this all up, if we fit a bell curve to the 20th century climate of the Southeast Fire Center, the southeast corner of BC, this is what it looks like, and there's the mean at 6.8 degrees Celsius. The model projections for the 2050s following the low emissions pathway are measured from the 1961 to 1970 baseline, and the projections are pretty consistent. They're around 2.6 degrees Celsius. And the take-home message here is that by the 2050s, even following the low emissions pathway, your average year in the southeast corner of BC is going to be warmer, or as warm or warmer than anything experienced in the 20th century, which is a dramatic jump. And when you think of 2.6 degrees Celsius, you don't think it would make that much difference, but that's a big change in terms of mean annual temperature. But of course, this is based on models, and there's a lot of uncertainty around models, so there's sort of a back of the envelope way to check this, if this even makes sense. Here we're looking at the last 50 years of mean annual temperature in this part of the world. It's been increasing at a rate of 2.8 degrees Celsius per century. The projections with the low emissions pathway by 2050 are 9.6 degrees Celsius, and if you simply extrapolate the rate of warming over the last 50 years into the future, it doesn't hit it in 2055, but it hits it in 2072, which for planning purposes is in the same ballpark. And this is important for two reasons. One is that it demonstrates that the climate model projections are not out of the realm of possibility. In fact, we've been living through that rate of change, or close to that rate of change, for the last 50 years. So in other words, the rate of change that we've lived through in the last 50 years gets us to a situation mid this century where your average year is as warm or warmer than anything in the 20th century. And the other reason why this is important is that often we're thinking in terms of climate change as something that will happen in the future, sometimes in the far distant future, but what this demonstrates is that the rate of change that is significant. We've already lived through that rate of change for the last 50 years. So I want to move into the question around, are we making progress in addressing this problem? And I'm going to zoom out again to the global picture. This is global mean temperature on an annual basis from about 1965 to 2021. And it's been increasing at a roughly linear rate. And there's been a couple of volcanic eruptions which cooled things down for a couple of years. But then you map onto that the 11-year, or roughly 11-year solar cycle. And that gives us a bump of about 1/10 of a degree Celsius. And you can see most of the warm years, many of the warm years are associated with the highs in the solar cycle. And on top of that, we've got El Nino, La Nina variations. And there's the El Nino, and it tends to be warmer during El Nino events and a little bit cooler during La Nina events. And so this explains a lot of the variation that we see in the recent climate history. But people who are keeping their finger on the pulse of this sort of thing are getting a bit concerned, because the last 7 years have been the hottest in the record, and some of the La Nina events are getting close or even over the long-term historic trend. It's too early to say whether or not this represents an acceleration of the global temperature, but there's some eyebrows raised about the recent years. But there's other metrics for addressing this, and actually some feel that ocean heat content is the better metric for addressing this, because most of the energy, most of the heat ends up being stored in the oceans, and I think it's in the 90% range. So the atmospheric temperature is kind of the tail, and the ocean is the dog. And here's the trend from 1970 to 2000. Here's a linear extrapolation from 2000 to present, and here's ocean heat content, which is above the linear increase. It's starting to look non-linear, in other words, increasing at an increasing rate. If we look at the world's glaciers, this is the cumulative mass balance of the reference glaciers around the world. There we're looking at 1970 to 2000, and there's the rate extrapolated into future linearly, and here's what glaciers have done around the world. Again, it's starting to look non-linear, decreasing at an increasing rate. If we look at Arctic sea ice, same thing. There's the rate from 1979 to 2000, and in recent years, it's been decreasing faster than that. And here's the one really key metric. We're looking at the concentration of carbon dioxide in the atmosphere. There's the rate of increase was fairly linear between 1970 and 2000, and there's been a lot of work done in recent years to try to deal with this. Kyoto Protocol, 26 COP meetings, the Paris Agreement, the Copenhagen Agreement. And the idea was to bend this curve down, or try to flatten it out. Here's the linear extrapolation, and here's what's happened. And again, this looks like it's increasing at an increasing rate. And unfortunately, we're not really going to get a handle on this problem until we start to bend this curve in the other direction. So can we turn this around? And here's where I'm going to get a little bit political. And also, there's a lot of uncertainty around this, because what happens in the future really depends on which emissions pathway we follow globally, and that depends on international politics, which gets into very sketchy territory. But we do know for sure where the carbon is coming from, and it's pretty simple. This is the contribution to atmospheric carbon dioxide from coal, oil, and natural gas. And it's pretty simple. If globally we continue to produce coal, oil, and natural gas, we're going to end up increasing carbon dioxide in the atmosphere. Now we have some, accounting tricks whereby we can produce oil in one country and sell it in another country and not have that count towards our national totals. But the atmosphere doesn't care about that. If we produce more coal, oil, and gas, we end up with more carbon dioxide in the atmosphere. And looking forward, at least for the short term, this doesn't look great. The International Energy Association, its Coal 2021 report, states that coal-fired power generation is set to reach an all-time high in 2021, and coal production is set to rise to its highest ever level in 2022. So for at least the short term, this is kind of heading in the wrong direction. If you follow the headlines in the Calgary Herald, you'll often see that production is projected to increase. Canada's set to smash oil production record in 2022, also heading in the wrong direction. Recently, our Minister of Natural Resources, Jonathan Wilkinson, has stated, and I think he pretty much nails it here. He says, there are many, many things that we have done to ensure we are supporting and actively promoting the interests of the oil and gas sector in this country, including the building of the Trans Mountain Pipeline. So that pretty much lays it out, that the government's on board with increasing production in the country, at least for the short term. And if you go to the government website, under clean fossil fuels, you'll see Canada's oil, natural gas, and coal resources, which it makes me scratch my head a bit, especially when you think about coal is far from clean. And when you look at Canada's oil, Canada is the fourth largest producer of oil in the world. And when you look at the carbon intensity of oil produced in Canada, it has the fourth highest greenhouse gas intensity. So far from clean, but the point here is that Canada is a major player on the world stage in terms of oil production. If we look at Canada's domestic greenhouse gas emissions, this is only including the upstream emissions associated with the oil industry. From 1990 to present, it's gone from about 600 million tons of carbon dioxide equivalent per year up to about 730 where we are now. In 1999, we signed on to Kyoto, and we were supposed to get down to 576 by 2012. That didn't work. And we signed on to Copenhagen. We were supposed to drop it down to 620 by, I think, now, and that didn't work. And recently, following the Paris Agreement, we've set a new target for 2030 at 523 metric tons of carbon dioxide EQ per year. And just in the last few months, we bumped that up to 430, and that's an ambitious target. But when you look at the projected upstream emissions that are associated with increasing production of coal, oil, just oil in this country, you have to add about another 100 million tons of carbon dioxide per year. So that means all other sectors need to get from 730 million tons per year to about 330 million tons per year in 8 years to hit that target. And I'll bet 2 six-packs now that we're not going to do it. So my hunch is, a strong hunch, is that we're not going to make our Paris NDCs, the nationally determined contributions, or our Paris targets. But we're not alone. A paper was recently published in 2021 by Perrin et al., which ranked countries according to their probability of achieving the Paris Agreement goals, and the countries in red have zero probability of reaching their goals according to this study. So it's not just Canada, it's many other countries, including some major fossil fuel producers. So looking at the projections from CAP, which is the Canadian Association of Petroleum Producers, and supported by the government of Canada right now, projections of oil production by 2035 are a plus 27%. And I think we're going to be heading in this direction. And that is, the reasons for this is basically the answer to the question that Justin Trudeau posed in a recent oil patch meeting just a couple of years ago, in which he says,
as I said on the very first trip to the oil patch back in 2012, no country would find 173 billion barrels of oil in the ground and just leave them there.
So that's pretty clear. And the answer to this question, which was unanswered, which everybody liked, is that no country is willing to leave their fossil fuel reserves in the ground. And when you think about it, he's got a point. Unfortunately, he's right. If we pull back on production, other countries will step in to fill that void, to supply the demand for oil in the coming decades. And this, in my view, is the nut of the wicked problem we face, and I don't really have an answer to that. I'm not sure how this is going to be resolved. And I've been called Dr. Doom on a number of occasions for being pessimistic, but frankly, I'm not all that optimistic that we're going to make our commitments to the Paris Agreement. If all countries met their Paris Agreement targets, we would limit global warming to about 2.7 degrees Celsius. And I'm afraid we're not on track to do that. I'll bet another 2 six-packs that, globally speaking, we're not going to make this target, let alone the higher emissions reductions pathways, SSP 1-1.9 or 2.6, that keep us below 2 degrees or even below 1.5 degrees. And that I think what this demands is that in the planning process, the precautionary principle demands that for planning purposes, we consider the high emissions pathways going forward that could lead to 3 degrees or 4 degrees Celsius warming globally by the end of the century. So to sum this up, Wally Broker was a climate scientist who worked for many decades and published many papers on climate science. And years ago he said, the climate system is an angry beast and we're poking it with sticks. And unfortunately, I think we are going to continue to poke that angry beast with sticks going forward. And we can do all we can to try to reduce emissions locally and convince governments to take steps to make significant reductions in emissions. But what we really need to do is do our very best to anticipate the climate changes that are coming at us and to take steps now to ensure that we minimize the impacts of those climate changes that we're going to be dealing with in the coming decades. All right, that wraps it up. I think we can now turn it over to questions.
Mel, thanks very much. Okay, so we are going to move into the Q&A. Thank you for the presentation. It's always good to have that big picture overview, like you say, a review for many people, I'm sure, but some updated data in there that, of course, just further accentuates your points. We'll see if anybody here takes you up on your bets for 6 packs. You might have some beer show up at your door. We'll see. So at the beginning, I recognize now that many of you watching today, or all of you watching, you couldn't see me. You still can't see me. We have the spotlight on Mel Reasoner. I'll turn my camera on such that you could see me just in a little bit, but I'll leave myself sort of in the background for now, and we'll leave the spotlight on Mel as we move into the Q&A. We do have some questions that are rolling into that Q&A box. If you haven't opened your Q&A box yet, why don't you do that and have a look at what's coming in there. If there are any questions that you'd like to hear an answer to, hit the thumbs up like I prompted or like we demonstrated earlier. What I'm going to do is read the questions to Mel so that he doesn't necessarily have to have all those screens up, and he might be calling on slides as needed to answer questions if helpful. So our first question, Mel, is from Aviva. And she says, how do you feel that organizations and communities within the Columbia Basin can mobilize change for climate action? A small question.
How do I feel about that? I'm highly supportive of it. I know some young people who are very much involved in this. And I think any action that can be taken to reduce emissions, either locally or nationally or globally, are steps in the right direction. And I think that even, when you recognize that the steps you take locally are a very small piece of the big picture, those little pieces add up. Brief answer to that question, I support the local actions that people are taking for reducing emissions in this part of the world. And I applaud especially the young people who are involved in that. And I hope it gets the attention of people who are in positions of power who are making decisions.
Okay, great. Thanks, Mel. Your next question comes from Robin Taylor. Regardless of the carbon scenario that comes to pass, we will need climate resilience measures. What are your thoughts on the key measures for climate resilience needed in southeastern BC?
Oh boy. Well, I mean, the one that really I think scares everybody, of course, is is the wildfire issue. And I think it was called the Philman Report, came out in 2004, which said that we needed to remove a whole bunch of fuel from around communities to safeguard those communities, basically fireproofing. And I don't think we've come anywhere close to the number that was recommended. But on the other hand, communities are starting to make progress on that. That's a big one. I did a postdoc in Boulder, Colorado, and I lived just outside of Louisville. Louisville was the community that burned a couple weeks back. I was watching TV going, I recognize that community. I jogged around that trail. The houses behind the trail were on fire. And no one expected wildfire to jump from a grass fire to literally a community fire. But it was all wind, and it just shows how destructive wildfire can be. So frankly, that's the big one, is taking steps to reduce the threat of interface wildfire, which is a huge hazard. And as we've seen recently, the extreme precipitation events have caused big problems in BC, and starting to think about how we can manage properties, infrastructure that are on floodplains, what we can do to protect those, because they are at risk. That is another big one in my mind. So I think, my view, the two big ones in terms of adaptation are minimizing interface fire risk and minimizing flooding risk.
Great, thanks. And I might just add that as the series goes on, I think that question that was posed will come up again and again, and I think the other speakers will add their 2 cents from an ecosystem perspective, depending on what their focal point is there. Thanks. Okay, so Ern Just, hopefully I'm pronouncing that properly. He says, can you explain the seasonal precipitation trends a little bit more? Is there a reason for increases in the spring and fall, but decreases in summer and winter?
That's a tricky one. The decrease in summer is projected, it follows the model projections. And I guess why that's happening is the model projections generally usually amplify what's already going on. So if you have a dry area, it'll get drier. If you have a wet area, it's likely to get wetter. And I think that applies seasonally. So in areas where you have high winter precip, you get more. In areas where you have low precip, you get less. And that's the case in summer in BC than the winter for high precip in BC. But the problem is with the model projections is that winter precip has been declining over the last 50 years a bit, whereas the model projections have been indicating it should be going up. So it doesn't always work very well with the model projections with precip. it's a harder thing for the models to capture. It's pretty good with temperature, but it's a little fuzzier when it comes to precip. So I'm not sure if that answers your question exactly, but when you look at winter precip, it's not, what's been happening is not what the models have been projecting. It's been going the opposite direction. That should, if, of course, the models are projecting into the future, that may turn around and winter precip may start going up. But over the last 50 years, it's been going down rather than up.
Okay, interesting. We have a question from Ross here. Are all climate stations in the Southeast Fire Center that you pull data from at Valley Bottom? Has there been any analysis completed on higher elevation stations, such as alpine or subalpine? If so, are the trends similar or more pronounced, less pronounced?
And this is a bit of a problem in BC because all of the climate stations, not all of them, most of them are at Valley Bottom locations, and all of the ones that I have in that analysis are at Valley Bottom locations. My guess is just about all of the quality controlled sites, the AHCCD sites, are going to be Valley Bottom locations. That's where you've had communities, that's where you've had met stations for the long term. There are a few exceptions. One is Glacier National Park, and there is a climate record from there that I've looked at previously. I didn't include it in this one because I think that record ended a few years ago. But over the period of time where it overlapped with the other records, of course, there was an offset. It was cooler because it's at higher elevation, but the trend was similar. But I would argue that it would be good to have more high elevation records of what's been going on with climate. And I'm straying into some territory that I don't know all that much about. There's a number of climate station networks. Minister of Transportation, Flun Road, BC Hydro have climate stations, and some of those are at higher elevation, but they're not all integrated. You have to go dig those out yourself. But also, many of the ski operations, especially the heli ski operations, have been recording climate change at high elevation for quite a few years. And I think it would be great if we could get our hands on that data. But that sort of strays into politics again. But the short answer to your question is all of the stations that I showed today were from Valley Bottom, and there is a paucity of climate stations from elevation, and it would be good to have that information.
Okay, great, thank you. Next question comes from Simone. Can you tell us can you tell us how the projections from the Okanagan differ from the Kootenays?
I'd have to go, to answer that question specifically, I'd have to go look at those numbers again. But we did some work in the Salmon Arm area and the Karamios area a few years ago. And from what I can just recall off the top of my head is that they were not dissimilar. I'm just guessing that the projections for 2050s for the low emissions pathway were in the 2.5 to 2.7 degree range, and they're around 2.6 in this part of the world. They're similar, but I can't without diving into some spreadsheets here answer that question specifically. But I can say with certainty that they're similar, but I can't comment on the details.
Okay, all right, thanks. Our next question comes from Jenny Fike, and that question's a little bit longer, so I've actually invited Jenny to speak, and she's going to share her question just now.
Hi, Mel.
Hi, Jenny. How are you doing?
Good. It's good.
I've been you for like 20 years.
I know. It's been a while.
Anyway, we'll have that conversation later.
Yeah. When I worked in the climate change field in the Ministry of Environment for the BC government, my focus was on climate change adaptation for nature. And I found that a lot of the scientists and civil servants that were involved in the climate change field saw any work in adaptation as taking away the focus, the funds, the priority from mitigation, like reducing the greenhouse gas emissions. It's almost like if you're in the field of adaptation, you're already admitting failure. And I didn't see it as being an either or a win-lose kind of discussion. A lot of us working in adaptation also thought that, of course, it's important to reduce the amount of CO2 in the atmosphere, but we had to face reality and develop and implement adaptation and resilience strategies. And I just like your views on how you're approaching it with your clients in terms of demonstrating that work in adaptation is not taking away from work in mitigation, but we need to do both.
Well, yeah, I'm with you on that, and I think it's almost in the work that we do with communities. I think it's kind of implicit. I don't know if I've ever explicitly said that one might be taking away from the other. I think, and I think I kind of highlighted it today a bit. Given what's happening globally, which is requires a top-down solution from almost an intergovernmental perspective on how we can collectively around the world start to reduce emissions. That is something that is out of our control locally, largely. But what is within our control locally is what we can do to anticipate what's coming, and the steps that we can take to ensure that the impacts are not as bad as they would be if we didn't take those steps. So, I mean, yes, the two go hand in hand, but I think the focus from a local perspective should be on adaptation, because what's happening globally influences the outcomes in terms of local climate, and B, we don't have that much control locally on how we can get the big emitters to stop emitting. So I think I agree with you. I think it should be made absolutely clear that adaptation procedures or strategies need to be put in place alongside mitigation strategies. We need to be doing both. And yeah, I kind of think that should be the message, that it's not one or the other, it's got to be both.
Okay, great, thanks. Jenny, you were muted by me, so sorry about that, but we're going to move on. So the next one is more just a comment. I'll share it out loud. Jacqueline, she says the federal government has a questionnaire that's been put out. Today's the last day she notes for Canadians to submit their thoughts and ideas on how to achieve net zero emissions by 2050. So that link to that questionnaire is in the Q&A if you want to find it there. We're going to move on to Michelle Griffith's question. She says, do you think, and Mel, you may feel like you've answered this in part already, so yeah, do with this as you may. What do you think would be the top ways for rural communities to develop resiliency for climate change impacts to come? What resources and actions are needed locally?
Well, one thing that I sort of touched on is some work that we've been doing with some local communities and local organizations, and that is to try to quantify the probability of exceeding thresholds. I kind of like this idea, and I showed a few curves where it showed that there's going to be a 3% chance of exceeding 40.7 degrees in Nelson by 2050 on an annual basis if we follow the low carbon pathway, and 10% if we follow the high carbon pathway. And quantifying the probability of exceeding those thresholds, and that can be applied to all sorts of stuff, from infrastructure operations. I think that is a useful step for prioritizing which infrastructure, which operations need to be addressed first. And initially, when you're thinking about what's coming at us in terms of climate change, it's a bit overwhelming. But if you can work out the thresholds where operations or infrastructure are impacted, and then sort out the probability of that occurring, then you can start to prioritize which ones you need to do first. So I kind of think a probabilistic approach to threshold exceedance is a good way forward for starting to deal with steps that need to be taken for adaptation. And more generally, from sort of a global perspective, you need to look at what's most vulnerable in your region, at least in general terms, and start to work on that first. And my feeling in this part of the world, and I might be wrong, but I think the big ones are wildfire, interface fire, and flooding are the big ones. So look at the big vulnerabilities, the potential big impacts first, start to work on those, and then perhaps within those start to prioritize based on the risk of exceeding thresholds.
Okay, great, thank you. This question comes from Tyne Baker. Hi, Tyne. What are some of the biggest infrastructure related issues most planners are anticipating?
Well, I think we had a graphic example.
Oh, you know what? Sorry, she says this is a repeat of previous questions. No need to answer.
Okay.
I didn't see that part. Okay. So well, let's move on.
Just a quick comment on that. We did have a pretty graphic example of the vulnerability of our transportation system just within the last 2 months.
Yeah, right. Excellent point. Okay. So are there any projections? This question is from Simone again. Are there any projections on how ongoing changes will influence the ability to produce food?
There are questions around that. And I think there's already been some impacts, and they could get a lot worse. Short answer is yes, and that's something we need to be looking at. And again, it's you can dive into the details, and I think many crops have climatic envelopes that they grow within, and you can start to look at, do the projections of climate take you outside of those climatic envelopes where that particular crop will grow? Then you can start assessing in your region, is it time to start thinking about growing something else here? And clearly food production is a very, very significant issue for humanity, and is potentially very vulnerable. And so taking steps to address that sooner than later is important in my view.
Okay, great. You'll like this question. I'm just jump down to that. So Ingrid Lipa, she says, where can people get more information about climate change projections in the Columbia Basin?
Oh, I know the answer to that one. There's a website, it's called the Columbia Basin Source, that both Ingrid and I worked on, which, but it's an excellent source for all kinds of climate information in terms of projections and climate history, like I've just been talking about, but also has a lot of information about what's been going on in terms of adapting to climate change and different solutions and steps that are being taken to address climate change. So Columbia Basin Source, or Columbia Basin Climate Source, if you Google that, you'll find it fairly quickly, and it's a very easy to use interactive interface that will lead you to all kinds of information about climate change in the Columbia Basin.
Great. Ingrid, why don't you put the link to the website in the chat for everybody to see right now? Okay, so it's almost 10 after 1. I think that I would like to close up in about 5 minutes. So let's just do 2 more questions. I'm just going in the order of upvotes here. So if I didn't get to your question, my apologies. So we have a question here from Wendy. It says, you suggest that if Canada lowers oil production, other oil producing countries will fill the void. What if people reduce their demand by changing personal behaviors such as driving EVs, not flying, eating a plant-based diet, starting the trend and passing it on?
That would, that's the way forward. How you do that is tough. And I think that in one, given the current scenario, that's maybe the only path forward. But we need to convince people all over the world that we need to start leading lower carbon or having a lower carbon footprint in our individual lives. That's a tall order. And in some countries, boy, even in Canada, there would be a lot of pushback on that. So politically, it's tough to achieve, but that would solve the problem. If people could be convinced to have a low personal carbon footprint around the world starting today, then we would reduce the global demand for hydrocarbon production, and that would start to bend the curve in the right direction. The tricky bit is, how do we do that?
Okay, great. So there's a comment here from Carl Clausen. Carl's with the Avalanche Association, I believe. And he says, not a question, but a comment here. And he says, I think getting historical high elevation weather records may be possible. MOTI has numerous high elevation weather stations many of which have been in operation for years. And I think that commercial recreation sectors might be willing to share their data. Some locations may have nearly 40 years of weather information. Yeah. So he's happy to assist you if needed, and I can send you his email address.
That would be great. Yeah, I think that would be really useful to have some more information from higher elevations.
Okay, great. Last question comes from Zane. Would you agree that in order to adapt to climate change, we must first understand what the risks are? If you agree, what mechanisms are available to assess and understand the risk? Have you heard of PIEVC protocol, for example?
Yeah, I was involved in a PIEVC project in Nelson a number of years ago. And yes, I think you're absolutely right. Prioritizing based on risk is key to sorting out what needs to be dealt with first in terms of adaptation. And some of the work that we've been doing helps with those graphs that I showed, helps to further quantify risk that can be plugged into the PIEVC process. Yeah, it's when it comes to adaptation, I think you need to do that. There's so many things that need to be addressed. You have to prioritize, and the only way to do that is look at what operations and what infrastructure are at most risk. That's a key part of the puzzle for sure.
Okay, fantastic, great, thank you. Kosta's going to pull up a concluding slide, and I'm going to take the time to thank Mel for your time. Thank you so much for all of the time and effort that you put in for us today, but also over the years, and for pursuing. We need some Dr. Doom. So thank you very much. Another round of thank yous goes out to you as well. So everybody in attendance, I know there's fewer people here than there were at the very beginning, but thank you to you for your donations. Once again, very much appreciated. Thank you to the Columbia Basin Trust for your support. Really is essential to have that bit of funding at the beginning to get this series off the ground. So our gratitude to you. And I wanted to just mention who we're going to be welcoming next week. I know that Mel did already, but we'll be having Dr. Brian Menounos next week. He's the Canadian Research Chair in Glacial Change and a professor at the University of Northern British Columbia. He'll be presenting a talk entitled Recent and Projected Changes in Snow and Ice in the Columbia Basin. So that'll be the same time, same day. So Thursday next week, noon hour. And if you've registered for this talk, you likely already have the link coming to you for the next one. Registration for Brian's talk is still open. So if you have any colleagues who you think might want to join, please get them to register with us before Monday at noon. And again, you can find more details on our website, cmiae.org. That's it for now. Thank you very much, everyone. We're going to end the webinar now.